Yeah, so I'm going to talk about the RVMC NOEL3, which is a new RISC-V microcontroller that we are developing in collaboration with ISA, as I will explain. This is our agenda. So yeah, this is part of the hardware-software ecosystem project, which is a project founded by ISA that's been done at Frontier Geisler. And we will develop this microcontroller, and it will be available as part of the ISA IP core portfolio. Also, we'll develop, starting from there, NOEL3 as a product commercially available from Geisler. These are the main characteristics of the core. It's 32-bit architecture, barrel processor, in order, pipeline, and deterministic. We have, of course, since this is space stuff, fault tolerance, and it has a small footprint. So it would work with very small FPGAs, which is something very useful for space applications. I will talk more about this later. So first of all, I'm going to explain what's a barrel architecture, because this is a weird concept that probably most people are not very familiar with. This is a fine-grained multi-threading processor, which means that every cycle, new thread comes into the pipeline. And once that thread finishes executing, it goes around. So we have as many threads as number of stages, and we change every cycle of thread. So as we can see, like in the animation, every time a thread retires from write back, it goes to like the retiring queue. So every cycle we retire different thread, and then we go around. So there we see the thread 0 is now retiring again, and it will loop around like a barrel. That's the name, where the name comes from. But what's the benefit of this architecture? We can get a very small area microcontroller thanks to this, because we don't have as many data dependencies as we have in a normal processor. We can avoid forwarding, no branch prediction, no general speculation. So it's very handy in that sense. Also makes it very, very easy for verification, because your each stage is kind of independent from the other, which is not as common in normal processors. Also, you have multiple threads, so each thread will execute one every nth cycle, being nth the number of threads. But the performance that you get in multi-cycle is very, very high, because you can run very high frequency, removing these critical paths. Yeah, so this is our primary feature set. It is represented as circle because it's barrel, so it goes around all the time. And we will have, as I said, in order pipeline, barrel architecture, deterministic execution, fault tolerance. The configurable number of threads will come from the configured number of stages. So if we add more stages, we have more threads. If we remove stages, we have less threads. We use 10-coupled memories for determinism, and also they will be configurable in size architecture to accommodate all the FPGAs with EDAC and all that stuff. Also, we have two buses, deterministic bus, which is a custom one coming from the APB standard. We are not compliant with it, but it comes from there. And then an AHB, non-deterministic bus, for connecting other type of peripherals. We have the RISC-V standard debug module, of course, to be able to test code there, which can be connected using Germon or third-party RISC-V debuggers. To be deterministic, we also develop a custom accelerator interface, which basically allows us to execute in time-bounded and every time the same amount of cycles. So if an instruction takes like 5 cycles to do divide, and we have 4 threads, we always wait to 5 times 4 threads cycles to ensure that it would have finished, and always we have the same amount of cycles being executed. Something very relevant in this processor, in this type of configuration, is having CSRs and also register file in VRAM, because we need to have one CSR copy and register file copy per thread. So if we accommodate that in flip-flops, especially for a small area processor like this, it would be very, very costly. So we have blockgram, CSRs in blockgram, and we will have scrubbing or that. I'll explain that later. So I've been talking a lot about determinism, but why do we need determinism? Determinism, it's very helpful for RISC-V real-time systems and for them to be predictable. What do I mean by that? So we can say, just by looking at the code, kind of, like the number of cycles that it would take to execute. And we are always the exact same number of cycles when we are executing, let's say, deterministic mode. In this manner, we need the threads to not affect each other execution time. Deterministic mode is not 100% of the time working because there are some exceptions. Like while you execute from TCM, you will be in deterministic mode. But if you access external memory, there is no way we can bound that time nor in a reasonable manner. So you will be outside of the execution, deterministic execution. Also for interrupts, you won't be deterministic when you take an interrupt, because since the instruction is, as I said, looping around the pipeline, you have some margin there of some cycles where the interruption can be taken. Also, if you are doing multiple iterations of the same instruction, which can happen sometimes, you have to finish that instruction until you get a new one to get interrupt. So we are talking in the tens of nanoseconds of variance between your interrupts, but it's still there, so we cannot say we're deterministic there. It's probably good enough for most people anyway. AHV accesses are not deterministic because it's not are non-deterministic bus to access like external stuff. How do we get determinism? We have a combination of a couple of things. First of all, TCMs, I've been talking about this all the time. Tight coupled memories allows us to be deterministic instead of memory caches, very complex. We have a deterministic bus interface that comes from APB standard. That way we can access and always return like in the same cycles. So we are bounded there. We can be deterministic while access is peripherals from the deterministic bus. And the accelerator interface for like shared resources. A good example is like square root or divide. Those you don't want to have like as many resources as you have threads. So what you do is you basically have one shared one and multiply and extend and wait for some like extra cycles to ensure that your bounded time is always fulfilled. This is some comparison of different configurations. The right one with all the feature set we don't have yet, we are in development, so it's to be done. But the medium one, which is like kind of the decent basic configuration for CoreMark, we have 0.9. This is per thread. So we have 3 plus 1. This would be multiplied by 3 if we're executing all threads. This set mul extension that we're seeing at top is basically M extension, but without the divide. It's just multiplication, basically. We are achieving in ultra-scale FPGA about 200 megahertz, and we are taking about 1.8 kilolutes, which is fairly small, I would say. How does this work with all the Geisler IPs ecosystem? We can connect basically all of them. That's why it's handy. You can take NOEL3 and do like a SOC in not that much time. So it's very useful. You can find more about that in the link there in Geisler GRLib IP library. We need fault tolerance for these space applications. Microcontrollers. So we are implementing single error correction, double error detection with EDAC, the embedded. We support 2 types, let's say. One that is like embedded in the FPGA, if the FPGA already supports it. And then we also have like a generic RTL based for like ASIC or other FPGA technologies. Of course, EDAC is not enough. So we also implement scrubbing in the internal. We have as I show here, is 3 plus 1 threads. That one thread, we are doing some scrubbing and internal processor stuff with that. So that will take care of that TCM scrubbing and the register file scrubber. And we'll correct the errors with EDAC. Finally, this connects, of course, with the RISC-V software ecosystem. So we have everything that is supported by RISC-V basically, but we plan to have some specific examples for multi-threading, like deterministic examples, and also we plan to be able to run Artems and Zephyr, which it's for real-time systems, so it's what we are aiming to be used for. Finally, this will be available in Q3 of 2025. As of right now, we have the RB32i set MMUL, the one that I showed for the core performance, and we are still developing, and also verification. So thank you very much. That's everything.